Hello everyone, my name is Ping-Seong Ku. Today I'll be presenting ThreadSense. This work was done during my internship at Dartmouth, where I was in collaboration with Qijia, Ziyan, Ziyan, and was advised by Shao and Xing-Dong. ThreadSense is a new sensing technique for one-dimensional touch input that works on an interactive thread less than 0.4 mm thick. It can locate up to 2 concurrent touches based on the principle of impedance sensing. Our motivation is that we want to bring interactivities to thin objects in our daily life, such as wirecrafts, embroideries, headphones, and even a hair-like sensor that can hide in the hairbreadths. This work builds and extends upon prior work in a number of domains, including capacitive and impedance sensing, and one-dimensional touch input on cord objects. For example, cord input integrates stretch sensor, rotary encoder, and conductive thread into a cord-based prototype, which enables sensing capabilities of how hard it is being pulled, how much it is being twisted, and where it is touched. And our cord enhances cords with movable slider control and touch input capabilities. They also combine AR glasses to visually extend the AR cord controls. In other words, IO-Brad creates an interactive textile cord with embedded sensing and visual feedback that can be integrated into headphones or drawstrings on garments. It can sense proximity, touch, and twist through a spiraling, repeating threading topology. Comparing with previous work, ThreadSense has the advantage that it works on very thin thread with a simple structure, which is a line of resistive material and cannot be supported by the existing method. Our method is also unique in that it locates touches based on a mathematical model describing the change in the impedance of the thread in relation to touch locations. Unlike many of the existing techniques using impedance sensing, our system does not need to be trained and only requires simple calibration before uses. To explain our sensing principle, let's first consider an evenly distributed resistive thread with both ends connected to an impedance sensor. By applying a voltage to the thread, the impedance sensor can calculate the initial thread impedance as the ratio of voltage drop and the electric current that runs through the thread. When the finger touches the thread, it shows a small amount of current to ground, which increases the thread's impedance measured. Take a closer look at the new circuit diagram. We can divide the initial thread impedance into two parts, ZH and ZL, with respect to the touch location. And we use ZT to represent the shunting impedance from the touching finger to the ground. Now we have a circuit diagram describing a touch event on an interactive thread. To express the changed impedance, we utilize a technique called star-to-delta transform to simplify the circuit diagram. After applying the transformation, the star network of a touch event on the left-hand side turns into the equivalent delta network on the right-hand side. Now the thread's impedance after touch can be estimated as ZHL, which is marked with the blue line. Note that the two impedances marked with red dotted lines won't affect the measured impedance and can be ignored. Based on the transformation formula, we can express the impedance change in terms of ZH, ZL, and ZT, where the value of ZH and ZL depends on the touch location. Here we can use a location coefficient alpha with a value between 0 and 1 to represent the touch location on the thread. For impedance ZT that marked with the green line, we can calculate its value beforehand with a one-touch calibration process. By asking the user to touch on a predefined position, such as the middle of the thread, ZT can be inferred based on the same transformation formula. Now we know ZHL is determined by the touch location coefficient alpha. This means the measured impedance of the user touching the thread can be used to locate the touch event. We can also track a two-touch event in the same manner. By performing the star to delta transformation twice, we are able to get a more complicated equation describing the relation of two touch locations and the measured impedance. To evaluate our approach, we developed a proof-of-concept prototype using an FDM 3D printer and off-the-shelf hardware and software. Our system consists of two parts, the impedance sensing board and the resistive thread. The main component of our sensing board is an impedance analyzer chip. We utilize a thread frequency method to return the real and imaginary parts of the measured impedance of the thread. For the thread part, we found through tests that total resistances between 500 kiloohms and 1 megaohms work the best for our impedance analyzer chip. Unfortunately, we cannot find any commercial product that qualifies our need. Therefore, we had to create our proof-of-concept prototype using an FDM 3D printer. We end up with a thread made of conductive filament with a 0.1 mm times 0.4 mm rectangle cross section. The thickness of the thread is limited by our 3D printer. To measure the accuracy of our sensing approach, we conducted system evaluations for both one touch and two concurrent touches. As the sensor is extremely thin and bendable, keeping it straight is important for us to accurately record the touch positions as the ground truth. For the study only, we printed the sensor straight on the supporting structure made of non-conductive material. Prior to the study, the system was calibrated for each participant using 1 and 2 fingers. To evaluate touches using 1 finger, participants slide their index fingers against the sensor as shown in the figure. And there is a needle that can point out the touch location. We recruited 10 right-handed participants. They need to slide their finger with a 2 mm sliding distance each time and complete the total 92 mm sliding distance for 2 times. To investigate the effect of calibration, we compare the sensing accuracy while varying the number of touch points used for calibration in a single touch experiment. Here we use average arrow distance to measure the tracking accuracy of our approach. The result shows a 6.13 mm arrow distance for 1 point calibration. And we were able to reduce the arrow distance to 4.16 mm with 5 calibration points. With this level of sensing accuracy, continuous input through sliding is possible, but the filter needs to be used to reduce noise. For the touches using 2 fingers, participants need to clip a 3D printed dividers to control the space between the fingers. We ask participants to center the target location in the middle of the index and middle finger. The 3 locations are the 1/4, half, and 3/4 positions of the thread. With the fingers set apart in the distance of 0, 4, 8, 12, or 16 mm from each other. Each trial was also repeated twice in the experiment. Our result shows an 8.55 mm arrow distance across the 3 locations and 15 touch points. Now I would like to talk about several conceptual demo applications to showcase ThreadSense and its capabilities, and highlight various usage scenarios. With ThreadSense, the user can hand out the form during the meeting by naturally touching the hairband, and change the form to minimal abstraction, which are much less interruptive. Another example is about wirecrafts. ThreadSense enables the wire bookmark, allowing the user to perform continuous touch input to the brightness of ambient light while reading. We manually soldered our thread sensor on an all-embroidered cushion cover, allowing users to touch different locations on the thread and trigger different actions. For example, tapping the French the first hour stance enables the microphone of the Alexa. Tapping the second hour using one finger turns on music. Tapping the same location using two fingers plays the news. Swiping on the dotted line changes the channel. This way, the cushion becomes the user's always available remote control. Now I would like to talk about our future work. The first thing is that we believe thread can be manufactured using fibers. One possible approach is to coat a fiber thread using conductive ink. Another possibility would be utilizing materials like conductive polycarbonate to create a thread. The challenge is in the requirement for the conductive to be evenly distributed along the thread, which requires a precise manufacturing process to overcome. From the calibration process, we found that the impedance profiles differ across the users. This is primarily due to the difference in their body impedances. Such individual differences can potentially be useful for differentiating input from different people. The key challenge lies in the fact that the measured impedance is affected by both user's body and the finger touching locations. We plan for future work to investigate methods that can separate these effects for user recognition. With that, I would like to conclude our work with 3 take-home messages. We discussed an approach to enabling one-dimensional touch sensing on an interactive thread. Our system utilized a mathematical model describing the change in thread impedance in relation to the touch location. We foresee that ThreadSense holds the potential for sensing techniques on extremely thin and soft objects. That's all of my presentation. For more detail, please see our paper. Thank you.